Alright, so up to this point you've learned 4 ways on how to solve a system of linear equations. You've learned to do it with the graphing method. You can do it with the substitution or elimination methods. That makes 3. The 4th way is Cramer's method, or Cramer's rule. And today you're going to learn to solve a linear system of 3 variables using inverse matrices. So let's get started.
So we'll begin learning about the inverse matrix by learning about the definition of the identity matrix. Just like in addition rules, you had an identity rule for addition, and that was you would add 0 to something. When you had an identity rule for multiplication, it meant you multiplied by 1 in order to get that number back out. So an identity rule for identity matrix is a matrix with 1s on the main diagonal and 0s everywhere else. So in the picture below, you can see the identity matrix for a 2 by 2 matrix. You would take your matrix and multiply it by a matrices where you had 1 on the diagonals and 0 everywhere else, and then you would get that original matrix back out. For the 3 by 3 identity matrix, again you can see the 1s on the diagonals and 0s everywhere else. And we will use these identity matrix in a little bit, but it's going to help us identify if we've truly found an inverse matrix. So let's move on to an inverse matrix. 2 matrices are considered inverses of each other if their product is that identity matrix. So let's write that down. And here's that definition. Now, it's important to notice that I wrote that their products in both orders must yield the identity matrix. So what that means is if you take matrix A times matrix B, those two would be inverses if their product was the identity matrix. But then it works in reverse too, it must. That if you have B times A, you also get the identity matrix. You should also know that for any matrix, if it has an inverse, it will only have an inverse as long as its determinant is not 0. And that's important to note right now. So I'm going to write that down. That a n by n matrix, which we'll call A, because I'm going to do a little something else here, only has an inverse if and only if its determinant is not 0. And let me move that over. Oh, I can't move it over. So I'll just shove it in there. Its determinant cannot be equal to 0. Hopefully you can get that in your notes. Alright, and so let's talk about the symbols for inverse matrices. There is one. And if you have a matrix A, its inverse, let's say you have a matrix A, its inverse is notated by A with a little -1 as an exponent. Now it's not really, it's just A to the -1, and you'll find that button on your calculator, but it is read that that is the inverse matrix A. Okay, so let's look and dig in at what the inverse formula looks like. If you're given a matrix A, and here are the elements A, B, C, and D, you find the inverse of it by taking 1 over the determinant of that matrix A, and then you follow this rule here. Look at what it's doing. It's taking what was A and D and they're swapping positions. So now D is first row, first column, and A is second row, second column. Those two numbers swap positions. C and D stay where they were in position but change to a negative. So you change the signs of C and B, but they stay where they were. And here they just write out the rule in more detail by throwing in the determinant equation for you. But it's important just to see what's happening here, that you have numbers changing positions and you have elements that are staying in their positions but changing signs. So let's start with example 1, and we will find the inverse of this 2 by 2 matrix. So you have matrix A, and you have 5, -2, 8, and -3. Your first step would be to find the determinant of it, but we can do it right inside of our equation. So let's begin writing the inverse of this equation. And we will say that our inverse of this matrix A is going to be 1 over the determinant of A. And then I'm just rewriting this down for ourselves. And D is now here, and A is over here, and C and B change signs. And we can use that formula from up top. I'm going to use this one right here if you wanted to do it all in one step. Otherwise, feel free to calculate the determinant off to the side and put it in. The determinant is found by taking the product of a times d, which is a negative 15. Oh, that looked wrong, didn't it? Let me erase. Negative 15 minus c times b. 8 times a negative 2, which is a negative 16. So you're done with that part of the formula. Next, we need to rearrange our numbers into this rule. So remember, D now needs to move positions. D was originally a negative 3 down here, second row, second column. It's going to go up here now. So I'll put a negative 3 up here. The 5 swapped positions with it, so it is now down here. 8 and negative 2 stay where they are, but switch signs. So now you will put a negative 8 here and a positive 2 there. So now what do we get? Well, our first part of the equation is 1 over negative 15 plus 16, which is just 1. And often you will get that first part being really neat. So it's 1 over 1, which is just 1. You could write that in front. You don't need to. And then you would just, this stays written down, and you have just found your inverse matrix, or the matrix that when multiplied to the original matrix would get you that identity matrix with the ones on the diagonals, which I will prove to you, I guess, here. So I'm just going to erase this 1. Oh, I didn't mean that. It's back. I wanted to erase that 1. So I'm going to, off to the side, prove to you that when I multiply these two matrices together, the A and the A inverse, that you truly do get the identity matrix. I don't really want you doing this. If it's going to screw you up, don't watch me. I just want you to, I wanted to prove to you that you actually get the identity matrix out. So this is just an extra little bit. So I will take our original matrix of 5, negative 2, 8, and negative 3, and multiply it by what came out as our identity matrix. And so I'll change that color, I guess. Here's my identity matrix, negative 3, negative 8, 2, and 5. And I will begin multiplying these out. And I'll just talk through it, I guess. So you start off where you get 5 times a negative 3, which is a negative 15, and then I will get plus 16. So negative 15 plus 16 is indeed a 1. Then to find first row, second column, I will take 5 times 2, which is 10, plus a negative 10. Well, that's 0. So far, so good. To find this element, I will take 8 times a negative 3, which is a negative 24, plus a positive 24. That's a 0. And then I will take 8 times 2, which is 16, plus a negative 15, and that's a 1. So hopefully now you can see how these work. If you take your original matrix times its inverse, which undoes the matrix in a way, if you think about it like that, you will get out the identity matrix. So let's practice finding the inverses of more matrices. And remember, this is just the building blocks to get ready to solve systems using inverse matrices. So you really need to understand this concept. All right, I will walk through guided practice number 1, and then I will leave you to do 2 and 3 on your own, but give you the answers. So looking at matrix 1, I'll just say A equals that. So in order to find the inverse of that, you need to take 1 over the determinant. So that would be 1 over 24 minus 2. So this will be more interesting now. And then you take your matrix and rearrange the proper elements. The 4 and the 6 switch positions. The 2 and the 1 stay where they are but become a different sign. So now you end up with the inverse being 1 over 22 times 4, negative 2, negative 1, and 6. This is a scalar outside in front of a matrix. So now you can clean up your identity matrix. And this will often happen where you just have fractions inside of there. Here, let me move this down here more so we can see it. So if I had the inverse matrix and I multiply that scalar, which is a fraction, 1 over 22, by every element inside, you're going to end up with 4 over 22 in your first element. And I'll leave it unreduced right now. So it's 4 over 22. This is negative 1 over 22. This becomes negative 2 over 22. And this becomes 6 over 22. And of course, this can be reduced, and you should reduce them if you can. 4 over 22 can reduce to 2 over 11. This one stays negative 1 over 22. This would be 1 over 11, negative 1 over 11. And then this one, when you divide it by 2, you would get 3 over 11. And that indeed is your inverse matrix. You can always check it to make sure you get the identity back out by taking your inverse matrix times your original matrix. You go ahead and do number 2 and 3, and I will list the answers for you. Pause the video. Number 2's identity matrix, A inverse. You should get the answer 2/3, negative 5 over 12, 1/3, and negative 1 over 12. For number 3, your inverse matrix should be much nicer looking. Negative 1, 2, 1/2, and negative 3/2. If you didn't get those, my number 1 suggestion would be to check that determinant. Something probably went wrong there. Make sure your appropriate elements switched positions and the right ones switched signs.